The program is called Homology, Theories, and Low Dimensions, and it's really about connections between different areas of mathematics. And the frame for studying those connections, in our case, is really about these homology theories that are related to knots and three manifolds.
Yeah, so I mean, one of the things that's great from my point of view about how these theories work is that they touch on so many different areas of mathematics. So we have people here who do algebraic geometry, who do representation theory, we have a lot of people who do topology, and so it brings people together from a lot of different fields that you wouldn't necessarily think, are working on the same thing, but then you find out that sometimes surprisingly that you are. Well, one of the things that I find sort of really exciting about it is that it brings together mathematicians from sort of lots of different areas that you wouldn't necessarily think are related. So you find that knot homologies are related to algebraic geometry and to representation theory and to physics and to, well, more obviously to topology. And so there are all these people here from slightly different walks of life, and it really gives you an opportunity to get different perspectives on the subject that you wouldn't have maybe just by yourself. One of the main things that we've been working on, which was kind of a gamble actually when we put it down in the application to run the program, is this so-called L-space conjecture, which is due to this man right here, and two other people who we've been very happy to have here, Cameron Gordon and Steve Boyer. And this conjecture relates three different things, which are, it's kind of surprising that they would be related in this way. And I think it's been great to have Cameron and Steve around, and we've all learned a lot and gotten a lot out of talking about these ideas while we're here.
Just to expand on that, one thing that this conjecture does is it makes predictions. So something that's natural in one area makes surprising predictions in another. And one example of this is the question about how heat flow homology behaves under covers. And in particular, there have been some questions kicking around about cyclic branch covers. And this is something that Cameron Gordon started thinking about, and I think it's gaining momentum, and in particular through a project of Cameron Gordon, Steve Boyer, and Michel Boileau, all of whom have been here. This is really starting to take shape, and a picture's emerging, and that's been something really exciting to see develop here in-house. One advance, I think, is to try to translate these sorts of questions into relative versions of the same problem, so into questions of manifolds with boundary. And this is a setting where techniques from foliations and from left-orderability were really leaving a big group of questions for Heat-Guard floor homology people to try and consider. And I think what's been really exciting is getting a better idea for what those objects look like, getting a better idea for the answers, and as a result, this is now feeding questions back in the other direction, kicking the ball, so to speak, to the foliation people. And I think the foliation people are really running with this, and I've been seeing talks about this. Really exciting.
Yeah, so just to amplify on that theme, so one of the things that's really exciting to me is that there's been a convergence in the way that we think about, on the one hand, in the sort of floor homology world, and on the other hand, on the representation theory world, how we think about these manifolds with boundary. And now we see that we should pretty much in all cases be thinking about, we have some chain complexes over a category, and you should interpret this in different ways. You can think about it algebraic geometry, you can think about it in terms of symplectic geometry, and yeah, it's been really great to sort of see that convergence on how we think about these things.
So the hope is that in setting up an atmosphere where there's connections being made and explored between different areas, is that tools from one area can be translated into another and then used to solve problems in another area. So maybe as a fun concrete example is in the case of this L-space conjecture, which is now known to hold for graph manifolds. Because you've got an invariant that you can calculate on the Hikaru floor side, this turns into a certificate for left orderability for groups that are associated with graph manifolds.
Yeah, I don't know if this is really an application or not, but maybe I should start this again. All right. So Liam told us about some sort of connections within different areas of mathematics. So another really interesting area that there are connections in is with sort of quantum field theory and high energy physics. And so it was great, for example, we had Kumran Vafa here to give a talk in one of our workshops. He was one of last year's Breakthrough Prize winners, and there's some really great work going on in the physics community right now about the structure of Chern-Simons invariants and how you should think about them. And that's, again, this isn't going to cure cancer or anything, but it is a sort of connection between these two worlds. I think it's sort of really great potential to see this connection.
So by design, we've been trying to set up an environment where impacts So by design, we've been trying to set up a program where the real impact is between different areas of math, and I feel like that's been very successful. But in particular, I think that's been successful because the environment the INI has set up for that has really been open. There's been a lot of activity between people, a lot of conversations happening. It's been a really positive space.